Okay, good morning. This is Professor David J. De Los Reyes. Okay, my topic for this morning is already April 15. The time is around 2:35. My topic is still advanced mathematics. This should be advanced math lesson number 31. Lesson number 31 is actually a continuation of lesson 30 because lesson 30 it was a very long one. We just completed the so-called computation of the unknown constant A. And the unknown constant A is the solution of the so-called complementary solution. So actually, the last time around, we just finished the so-called complementary solution. So for this morning, April 15, we will be bringing out the computation of the unknown constants B and C to compute for the particular solution. Okay, let's proceed. Our topic for this morning will be Advanced Math, lesson number 31. The title is Continuation of Lesson 30, the continuation of the solution, so-called particular solution. The particular solution, I sub P. The last time around, we have computed for this. It was a very long, it's not so long, but the algebraic manipulations involve so many steps. So actually, we have computed already for the value of A. We are considering for the meantime an RL-AC circuit. Okay? Resistance, inductance, energized by an alternating current source. The problem is asking for I as a function of time. So actually, the total current is the sum of the complementary plus the particular. And for Laplace transform solution, I separate the complementary from the particular because it involves three unknown constants A, B, C. And the last time around, we just finished A. So for this morning, we will compute for the value of B and C to bring out the particular solution. Okay? So, we are still considering an RL-AC circuit, ladies and gentlemen. Okay? Let's continue. From the previous solution, after we take the Laplace transform of both sides after taking the summation of voltage equal to 0, what comes out is actually an equation E sub m over L times the quantity S sine of angle P plus omega cosine of angle P equal to, I place it on the right hand side. The solution should be by using the so-called partial fraction because the left hand side involves three linear factors, and the three linear factors are actually S plus RL, S plus G omega, and S minus G omega. The sum of S square plus omega square is actually factorable to S plus J omega times S minus J omega. Okay? There is a factor on the denominator for the left hand side, that is S square plus omega square plus this. So if we try to simplify this one, for the ordinary mathematicians, you cannot solve this one because this is higher mathematics, that is S square plus omega square is actually factorable to two linear quantities, S plus G omega, S minus G omega, where the value of G square is equal to minus 1. Or in mathematics, okay, because this is under electrical engineering, G square is actually equal to I square, and they are both equal to minus 1. But for the meantime, since we are on the topic electrical circuits, we will use G square instead of I square. For I square, this is for mathematical purposes without reference to electrical circuits. But if we are considering analysis of electrical circuits, we will be using G square instead of I square. So I will remove this one, okay? Because if we try to expand this one, S times S is actually S square. The middle term cancels because the middle term is G omega S minus G omega S. It cancels out. And the last part is actually minus G square omega square. Then we try to replace this G square by minus 1. Minus 1. Okay, so this is minus minus, it will now become plus. So meaning, S square plus omega square is actually the linear factors S plus G omega, S minus G omega. Okay, I will try to erase this one. Okay, it is this. We have computed for the value of A. And actually, we have computed already for the complementary solution. For an RL-AC circuit, by using the differential equation, if you try to recall back our total solution the last time around, this is our total solution. This is the so-called complementary solution. We have done that the last time around. So what is only missing is actually the particular solution, that is the equation A sub m over Z times the quantity sine of omega t plus angle P minus angle theta. There is a minus sign over here, and this minus sign refers to lagging. Okay? If there is an inductor, the current lags the applied voltage by a certain angle theta, that is minus angle theta, where angle theta is actually the arc sine of omega L over Z, or the arc cosine of R over Z. So if the load or the companion of the resistance is an inductor, we could say that the power factor of the circuit is actually a lagging circuit. So the significance of this negative sign here means that the other load is actually equal. Okay, let's try to continue. Since the last time around, when we put S equal to negative R over L, we have computed, we got the algebraic manipulation, it almost consumes half of the word, right? And we have computed that the value of A over here, is minus L over Z times sine of the quantity of angle P minus angle theta. And actually, after we have computed for the complementary solution, what comes out is actually I sub C is E sub M over Z sine of the quantity angle P minus theta plus quantity E raised to minus R over L times time. There's a time over here. So meaning the complementary solution only occurs for a certain period of time. But for the particular solution, as you will see, okay, there is no exponential thing. Okay? Okay, let's try to continue. To compute for the so-called particular solution, we must have to compute for B and C. And for B and C, I place it here. When S is equal to J omega, we put it here. A will become 0, B will become 0, and C is actually the one we could look for. Okay, because when S is equal to J omega, this will become 0, this will become 0, and we could solve for this one. Okay, so going back to this equation here, we replace S by J omega. J omega, okay, I expanded already. J omega sine of angle P, okay, plus omega cosine of angle P, this should be equal to 0 plus 0. These two are zeros because if J omega is actually, if J omega will be, if S will be J omega, we will multiply A and B by the difference of this, that is J omega minus J omega, and this is equal to 0, right? So it's 0 multiplied by A and B, automatically A and B will be 0, so we could compute for C. So the right hand side will now be 0 plus C, and when this will be the resulting equation, right? This is the multiplier. And substituting the value of S to be equal to R over J omega. We replace S by J omega, so C times open quantity J omega plus R over L plus times the quantity J omega plus J omega. So as you can see it, when S is equal to J omega, C will be computed. But for A and B, they will become 0. So if we try to simplify this one, it's just algebraic manipulation, guys. C will be equal to L over 2J times the quantity cosine of angle P plus G sine of angle P times the quantity R plus J omega L. And again, simplifying further, I will check my camera. It's just algebraic manipulation. L over 2J cosine of theta plus G sine of theta, by using Euler's equation, it will be E raised to the plus J theta. Okay? What remains on the bottom will be 2J and R plus J omega L. I will try to multiply the numerator by 1 over Z, and I will try to multiply also the denominator by 1 over Z. Okay? So if we try to simplify the resulting equation, L over 2J, this will go down, times 1 over Z, open bracket, A raised to J theta. I'm just following this. Okay? I will try to distribute this here inside. So it will become R over Z plus J omega L over Z, close bracket. And if we try to bring out the, what we call this, impedance diagram for an RL circuit. For an RL circuit, the real part is R, the resistance. The imaginary part is X of L. This is actually X of L. X of L is actually omega L. The natural frequency of oscillation times inductance. Okay? So this is R, this is X of L, which is omega L, and the resulting, what they call this hypotenuse is the impedance. So actually, the angle between R and Z is represented by theta. This is angle P, different, it's different from angle theta. So if we try to take the cosine of theta, it should be R over Z, and sine of theta will be omega L over Z. So actually, we could replace this one, R over Z, by cosine, and omega L over Z by sine of theta. So actually, the resulting denominator, after the replacement, it will just become cosine of theta plus G sine of theta. And again, using Euler's equation, A raised to J theta is actually cosine of theta plus G sine of theta. Okay? So what will come out? C now will be, I will just copy this one, L over 2GZ times, open bracket, A raised to J angle P, all over A raised to J angle theta. Then by using the so-called laws of exponent, we bring up this one. So it will become L over 2GZ times A raised to JP times, if we bring it up, the exponent will become negative, E raised to minus G angle theta. And again, using the laws of exponent, same base, different exponent, so it should be same base, plus the sum of the exponent. J, open quantity, angle P minus angle theta close quantity. That is, C is equal to L over 2GZ times this exponential thing. Okay? It was simplified by using Euler's equation. Instead of using the sine and cosine, we compress it by using Euler's equation. So actually C is actually L over 2GZ times E raised to J, open quantity, angle P minus angle theta, close quantity, close bracket. So actually, we now know the value of C. So we are almost halfway through the so-called particular solution. Because as soon as we know the value of B, we will just combine this one, and what will come out after the algebraic manipulation and taking the inverse Laplace, we will bring out the particular solution. Okay, let's try to compute for the value of the other constant. We now know A, we now know C, right? So the only remaining that is unknown is actually B, this one. To compute for the value of B when S is equal to minus J omega. The first one is plus J omega. To compute for the value of B, we will put S to be equal to minus J omega. So A will become 0 and C will be 0, and we could compute for B. Because the multipliers of A and C will become 0. Right? Right? Because if this is minus J omega times J omega will be 0, okay, it will be multiplied by to C and A, so there will be, I put it here, A and C will be 0, that is when S is equal to minus J omega, and we could compute for B. So substituting, minus J omega sine of angle P, omega cosine of angle P equal to A will be 0, C will be 0 when S equal to minus J omega, but the value of B is not 0. Because the multiplier of B is actually the quantity S plus RL, close quantity, times the quantity S minus J omega. Substituting the value of S to be equal to minus J omega. Okay. This is just this. The right hand side will be B. When S is equal to minus J omega, this S will become minus J omega plus R over L, close bracket, times S minus J omega, but when S is minus J omega, this will become minus J omega minus J omega. Okay, this is the simplification. Okay, this should be equal to B, the one we are looking for. We multiply omega, J omega by L, so it will become minus J omega L plus R over L, close bracket. J omega minus J omega, two terms, right? So this is minus 2J omega. Actually, this W here cancels. Okay, so what remains will be, but there is an L on the bottom. So if we try to simplify, this will go to the left. So the left hand side will be L times the quantity cosine of angle T minus G sine of angle P equal to B. I will try to rearrange this one, R minus J omega L times minus 2J. W cancels out already. And if we try to compute for the value of B, B now will be minus L over 2J. This will go down, right? This negative will go to the left. You just multiply this one by a negative thing. Negative 1. So this will now be equal to negative L over 2J. Okay. This one is A, using Euler's equation, A raised to minus J theta. If this is minus, this should be minus, right? Times open quantity. What remains on this portion will be 1 over R minus J omega L. It is this one. Then again, as from the previous one, I will multiply the numerator and denominator by 1 over J times 1 over J. So if we try to simplify, this will go down, right? Minus L over 2Gj, A raised to minus G angle P, open bracket, 1 over. I will try to put this one or divide this one to these two terms here. So R over J, it will be R over J, minus J omega, omega L over J. And again, you replace this one by cosine, and you replace this one by sine. So what will come out? B now will be minus L over 2Gj, I'll just copy this one, E raised to minus G angle P, times open quantity 1 over cosine of theta minus J sine of theta. This is angle P, this is theta. They're different, right? Theta is the angle between the resistance and impedance. And this angle P was from the equation of the given alternating current voltage. So simplifying, it will be minus L over 2Gj times E raised to minus Gp times 1. This one again, using Euler's equation, that is A raised to minus J theta will be cosine of theta minus J sine of theta. If this is minus, this should be minus. So this is multiplied by 1 over E raised to minus J theta. So we compress this one by using Euler's equation, and the equivalent will be e raised to minus g theta. And simplifying further, they should be minus L over 2gj a raised to minus j angle p times, we bring this up. So if we bring it up, this negative sign will become plus. So this is multiplied by a raised to j theta. And again, using the laws of exponent, same base, so it should be same base plus the sum of the exponent. Okay, that is from Mr. Black Pen, Red Pen, right? B now will be minus L over 2gj times open quantity e raised to, I factor out minus j. Okay, this is minus. The first one is minus j angle p, and minus j plus minus theta is actually plus. So actually the sign outside is negative times open quantity angle p minus angle theta. So the value of b is actually almost similar for the value of c. What's the difference? The difference is in the sign. You see it? They are almost the same. And except for this negative sign also. So we now know the value of b. Okay? And since we lack space for tonight, I will bring out the algebraic manipulation of the value of b and c to bring out the particular solution for an RL-AC circuit. And actually, if we try to put b and c back here, then try to algebraically manipulate, then take the inverse Laplace transform, what will come out for the particular solutions will be a sub m over a times the quantity sine of the quantity omega t plus angle p minus angle theta. If the component or the companion of the resistance is actually an inductor, this should be minus. And the significance of this minus here is lagging, meaning the load is an inductor. It could be a motor load maybe, right? So the significance of this negative sign here, the companion of the resistance is actually an inductor. Okay, that's it, guys. I could not present the algebraic manipulation of B and C to come out with this. So the next time around, I will bring that up. So it will be lesson number 32. So lesson 30 is a very long one. They say Laplace transform is a simpler solution than the so-called differential equation. But in reality, the solution is longer due to the so-called algebraic manipulation. Okay? So I repeat it before we go for this morning. The total solution for an RL-AC circuit will be E sub m over z sine of the quantity omega t plus angle p minus angle t closed quantity minus E sub m over z sine of angle p minus theta closed quantity e raised to minus r over L times sine. We have done this already. So the next time around, I will bring out this one since we now know the value of B and C. Okay, that's it. So for you who are taking up advanced mathematics, this is for you guys. If you want to subscribe to my channel is at youtube.com/@proofdavidj.Reyes. If you want to share it, please click share. This is my fourth long-form video on my channel. So I am done with differential calculus, I am done with integral calculus, I am done with differential equation. So this is the fourth one. It's a long-form video. So if you are needing a guidance on these subject matters, this is for you guys. Good morning from Los Angeles.